So yeah, recording has started. So just a brief introduction about myself. Yeah, okay, well, somebody's asking for live transcripts. Okay. Okay, so just a brief introduction about myself. I'm Cho. I'm a year 3 computer science major at NTU. And I guess the reason that I'm holding this workshop is because in my previous internship, in the previous summer, I actually did Detectron2 as like the main, I actually used it as like the main library for the task that I did. So I think I'm in a good position to be sharing about this library and how we can do object detection and image segmentation with this. So that's a brief introduction about MLDA, and this is pretty much a template slide that we are given. So what MLDA is that it is pretty much a CCA that aims to teach people and like learn together about machine learning, data science, AI, and other stuff. And we also have several events that are actually going on almost throughout the entire year, be it from like all these workshops, which happens almost on a weekly basis. And we also have a deep learning week coming up very soon. So sign up for that if you haven't yet. And we also have hackathons and panel discussions and other really cool stuff related to AI. So, and as for the aims and the scope for this workshop, since you guys signed up for this, you guys probably saw the email or the LinkedIn post. So I would assume that you guys actually know some sort of image classification or have done a little bit of, machine learning or deep learning before. So you guys probably will know Python, and you guys have the basic idea about what goes on in a machine learning model, and that we need data, we need to have data sets, so we need labeled data sets to feed into the model to train it. And you will also know that, let's say for image classification, you need to label it, let's say for cats, for images of cats and dogs, you have to label each image, either a cat or a dog. And so this workshop will actually expand upon that knowledge and bring in object detection and instance segmentation to it. So what this workshop will not cover is any heavy theory or any math, because from previous workshops, the feedback that I got about other workshops from my other friends who attended them were that there was too much math and people would just zone out once they start seeing math and like equations on the screen. So this workshop will not have any math unless you want to see the slides. Then there will be optional slides that I will send out later eventually. And there will also not be any coverage of what goes on in like the source code of the actual library that we're using. And that's more for you guys to explore on your own in your own time. So what this workshop will cover is that we will first talk about what object detection and image segmentation is in a more formal terminology. And then we will talk about the dataset format that we need. And we are going to choose one dataset format, which is the COCO format, and expand about that. It is one of the more industry standard dataset formats that is currently used for detection and segmentation tasks. And then we will also have a live demo of data annotation, where we will try to annotate a few images, be it for object detection or instance segmentation. So for this part, I hope that you guys actually saw the reminder email where it was written that you guys, if you guys want to follow along, then you guys would have need to actually install two software, which is Label Image and Label Me. But if you guys don't want to, it's fine as well. You can just watch what I do. And eventually the annotated model will actually be, the annotated data set will be given to you guys in the course of this workshop. And then we'll be talking about Detectron2, and we'll try to train either object detection or instance segmentation model using it. And then I will talk about how we can actually deploy this model that we trained and try to visualize the results from there. So moving on, if anyone has any questions along the way, just put in the chat. So the next section is now to talk about what object detection and image segmentation is all about, right? So what you will see here is pretty much the end result that we want. And this is actually the image that is usually shown for the Detectron2's libraries. So for this part, what detection is that we want to actually detect whether an object is in an image or not, and like the different parts of the image and like how many objects there are. And then for segmentation, you want to pretty much just trace out the actual outline of the object instead of just a box around it. So in more formal terms, what object detection will do is to draw bounding boxes. And we call them bounding boxes because it is like the object is bounded within the box itself, right? And then the model will try to draw these bounding boxes around these objects that it identifies. And then to train this model, what we will need beyond just a typical image and like a single label is that we will actually need to give the coordinates of the bounding box and also the label for each box. Because like unlike typical image classification when there's only like usually one object in an image, here there can be multiple objects. Like you can see here like there's like 20, 30 people inside the image, and like there's other objects like bicycles, bottles, and like backpack, etc. So you would actually need to define all of these bounding boxes and these objects inside the image and give it to the model. And there are several methods of actually doing this, but today we'll be covering one particular method called faster RCNN that Detectron2 implements in a very nice and easy to use manner. As for image segmentation, what it actually is that it goes beyond object detection. It goes beyond just drawing a box. So instead of a box which requires very few coordinates to actually define, instead we will actually need to define the outline of the segment itself in this case. So this would pretty much be the XY coordinate of each individual pixel in the outline. So and these XY coordinates, when you join them together, it will form a polygon of sorts. And there are several different types of segmentation that's currently used in industry, which is semantic segmentation, instance segmentation, and panoptic segmentation. So today we'll be actually going through instance segmentation, and I'll actually talk about the differences between these three. So as you can see, right, in the three different segmentations, for semantic segmentation, you would see that all of the cars in the image are colored blue. So, and like the people are colored red, the sky, everything is colored. While for instance segmentation, like individual objects are colored differently. So the difference between these two is that for semantic segmentation, it will aim to actually like label every individual pixel and assign it a particular class. Like let's say it's a pixel of the sky, that it will actually label it as sky. And then it will actually just color all of the pixels that are labeled sky, the same color of, that in this case, light blue. And as for instance segmentation, the difference is that here, they will actually like distinguish between individual instances. So you can actually count the number of cars, the number of people inside this image. And it doesn't aim to actually label every single pixel in the image itself. And as for panoptic segmentation, it's kind of like a best of both worlds scenario, whereby we actually label every single pixel of the image and also label individual instances. So you can distinguish between everything that way. All right, so if anyone has any questions, just put it into the chat as usual. Now we'll actually move over to dataset formats and annotation tools. So for dataset formats, like I said earlier, you can't just give a class to an image and that's it, right? So what you will need to do is to give the bounding box coordinates for object detection, and you will actually need the point coordinates for the polygon for instance segmentation. So what you actually see in this case here, right? This is actually an image from a competition on Kaggle, which is a data science platform. And also like for the different bounding boxes that you can see here, these are actually like hand drawn by me like a few days back. So we actually, so the aim for this image was to actually identify these things that they actually term as maze heads. So these are basically the parts that turn into the corn or the maze or whatever things that you see. And as for this side, this is for segmentation, right? So we actually try to like draw a polygon around each particular tomato. And then we want to actually identify the individual tomatoes in the image itself. So how we actually do this, right? It would be very tedious to actually do this in terms of like manually like finding all the coordinates and stuff. So of course, there's software to help us. So these two are actually specialized software that I actually mentioned in the reminder email. So there's Label Image for object detection and Label Me for instance segmentation. And these are both open source software, and like there's like tons of stars for each project on GitHub. And like a lot of people use it for their own like side projects or personal projects. And they are actually like really straightforward to use. So I'll be showing them later on. But before that, this slide is a little bit quite cramped, but just bear with me. So we have to go through this COCO format first. So COCO format is a format for the data set that we actually feed into the model itself. So for this COCO format, the special thing about it is that all of the annotations, all of the object instances that exist in the dataset, right? Everything is contained in just one JSON file. So this JSON file is kind of like an all-encompassing file that contains all of the data, all of the segmentation, all of the categories, all of the bounding boxes, everything inside there is all like perfectly packaged for you. So there are scripts to actually convert between different formats, but one of the more popular formats is of course COCO formats. So and there are three main sections. There's images, annotations, and categories. And these are the three sections that must be present in that JSON file for whatever library to actually make sense of the data set. So I'll go through these three categories so that we can see what we can get data on as well. So the very first one I will go through is categories, which is the one at the bottom. For categories, right, what we have is basically a list, and each category will have a dictionary of sorts. So it will have a category ID and a category name. So let's say for like, in this case, it's an echo dot, but it can be like tomato, corn, or it can be a cat, dog, or whatever thing that you can think of. And as for the next thing, this is images. So it's kind of similar to categories, whereby each image has its own dictionary of sorts. So this one dictionary belongs to one image. So in this case, this is like the file name. So this is basically the file path of the image itself. There's the height and the width, and also a unique image ID. And this goes on for like all of the images in the dataset itself. The next thing is for annotations. So for annotations, these correspond to the individual annotation, the individual objects or segments that you will see in an image. So for this one, right, so there will be a unique annotation ID, and then it will also have a category ID, which corresponds to the ID that you see in this categories list. And then it also has a segmentation, which is basically the XY coordinates of the individual pixels that make up the outline of this particular segment. So it's a super long list, which I just like added on for this case. And then it also has an image ID. And this image ID actually corresponds to the individual unique image ID that you see in this images list. It also has an area, which is not really that useful, but it's like automatically calculated, so it's fine. And then we have the bounding box, which is basically the bounding box of the object itself. So for segmentation datasets, they will also have bounding boxes because it's really quite easy to compute using a script. Since like it's just the most extreme points of the instance itself. And the format that they follow for the bounding box, how they define this box, right, is that they define the top left corner in the first two numbers. So this is the top left x coordinate, and this is the top the top left y coordinate. And here, this is the width of the box, and this is the height of the box. So it's x min, y min, width, height. So it's just 4 different floating point numbers there. And this will actually pretty much define one particular annotation. And there can be multiple annotations, and like in a typical data set, there will be like what, thousands or like even perhaps like millions of annotations there, depending on your dataset type. And there are also other formats like YOLO, VOC, and other software-specific formats. And the two software that we are using today, called Label Me and Label Image, actually saves in either their own format or in the VOC or YOLO format. So eventually, when I send out the materials, I'll actually provide you guys with the scripts to convert between these different formats as well. So any questions? Let me look at the chat. There's one. May I know where I can access the other MLDA recorded workshops? Okay, so for this one, I believe they will eventually either send it out or they will actually upload it on YouTube, but stay tuned because I think it's still being processed or something. But besides that, okay, there's one more question. Can Detectron2 achieve real-time like YOLO? So no, it can't, because Detectron2 doesn't implement the YOLO algorithm. So Detectron2 actually implements the faster RCNN or the mass RCNN algorithms, and these are actually not real-time. But if you want to make it like maybe 1 frame per second, then it's fine, but definitely not like 30 FPS or 60 FPS in this case. But the advantage of faster RCNN for Detectron2 is that it actually achieves a somewhat better performance compared to YOLO. And another question is that, what is the difference between OpenCV and Detectron? So OpenCV typically is a classical computer vision implementation, which means that it does not make use of deep learning or machine learning for that matter. And it actually makes use of like very classic computer vision algorithms to do like detection and stuff. While for Detectron2, they actually make use of deep learning, such as like deep learning models like whatever I mentioned, like ResNet or Mars RCNN. So that's the main difference between these two. And typically, OpenCV models will have a lower performance compared to Detectron2 or YOLO algorithms. All right. And what is the difference between TensorFlow and Detectron? So TensorFlow and Detectron, the difference is that, okay, so TensorFlow is a framework for deep learning in general, while Detectron2 is a framework that is specifically for object detection and instant segmentation. So TensorFlow itself has its own object detection and segmentation API, but it tends to be much more complex to implement, and like it's typically more verbose. Like you will see how Detectron2, right? It will actually like make things a lot more abstract and a lot more high level to implement. So it's like easier and more purpose built for these purposes. All right. So I think that's all the questions in the chat so far. I'll move on. Wait, that's one more now. Oh, okay. Thanks. Okay. So now we'll be moving on to download the try data sets and some scripts. So if you guys will either scan the QR code or go to this tiny URL like link, you guys can actually download the data sets and the scripts that we need to actually do this. All right. So I'll give you guys around 1 minute to go and scan or like go to this link. If you guys have any trouble, just let me know in the chat. And then after that, I will stop sharing screen and share my entire desktop to go through with you guys as well. Okay, I hope you guys have managed to download or like just go to the link for now. The link is also in the chat if you guys didn't catch it. So for now, I will stop sharing and start sharing my desktop itself so that we can actually do it together. So share screen for sharing. You guys see my screen? You guys see my whole screen now? Okay, can. Okay, so let's go to my actual thing. So this should be the example that we actually went to. So we save it. We actually downloaded it already, so I'll just overwrite it there. So let's go to this. So we can first unzip it. I hope I'm not lagging on Zoom, but it should be fine. So I'll just unzip it here. So let me rename this thing first. So this is what you guys will see in this case. So we have corn annotation example, scripts, and tomato annotation examples. So for this particular thing, right, we have two data sets. So for the corn data set, it will be for detection. And for tomato annotation data set, it will be for segmentation. So let's start off with the corn annotation example. So we will go into unlabeled. So these 5 images are not labeled yet. So if you guys have actually installed label me or label image earlier, like I said, you guys can actually follow along. If not, you guys can just watch it, I guess. Okay, so we will go for label me. So just label me would do. Okay, so this is for segmentation. So label image is for detection. Let's do a detection first. So in your command prompt, right, if you guys have installed it, just type label image, label img, and this thing should launch. All right. So I'll just wait for a while for whoever wants to follow along to open it. No, okay, I will continue. So now let's just go to this open directory in this UI. So we'll open the directory. So for opening the directory, right, it's simply going to the con annotation example, unlabeled, right? Then select the folder here. It might be a little different if you're on Mac or Linux, but it should pretty much be the same UI, I guess. So once you open this thing, what you will see are basically the file lists in the folder here on the right. So you can export the different images also. And then as for this particular case, what you will see here is this thing. So now the objective for us to annotate this image is to actually tell is to actually like annotate where the con heads are in this case. So what we'll be doing is to create a rectangular box. So it's here. The shortcut to do this is also to press W on your keyboard. So all we have to do to annotate is to just click and drag. And then here we'll be calling it con. Then we click OK. So you see it shows up as here. So this corresponds to this particular box here. But of course, if we don't want to be typing con every time, right? So we'll just use the default label here and just say it as con. So it will just automatically do it for you. Then so now we press W again for a new box here. Okay. And after that, we'll just like click and drag all the cons that we can find. So typically, in most industry research or like deep learning projects in the industry, the thing about data is that it takes a lot of time to prepare data, to label and clean data. So according to some studies, it says people say that maybe like up to like 70% of the time spent in like working in industry for like AI stuff is spent on data labeling and cleaning. So you can imagine the amount of grunt work that goes into such things. And this is an example of the stuff that you have to do in industry, or if you don't have if your company is not big enough, unfortunately. If your company is big enough, then sometimes they will have their own annotation teams to actually label the data for you. So once you think that you have captured all of the con, you can just Control S or just press the save thing, and then it will save it as an XML file here. Okay. So it will actually save it in the same folder as the images itself. Then let's go for another one. This is a very simple one. So we just press W again. Let's click and drag, click and drag. So the boxes, right? It doesn't have to be like perfectly aligned to each object that you want to actually label, because like the model will usually perform well enough that you don't have to be like perfectly labeled, but the closer it gets to being like a perfect bounding box, the better the model will be. But if you're not looking for like super high performance, just a general proof of concept, it's okay that you just do it roughly. And it's okay that your boxes, right, are overlapping with one another, because in real life as well, you will see a lot of objects that are overlapping or like being occluded by other objects. So that's fine. And we'll just save it here. Let's just do one more image, perhaps this one. Then after that, I'll move over to the scripts and how to generate the Cocoa format from here onwards. So we will just have these formats. So when I was doing my internship on computer vision, and before I was able to use Detectron2, I actually had to label all these images, and it was like thousands of images, and it was really tedious, but that's part of the work, I guess. So yeah, let's save it. So now we actually labeled 3 images. Like you can see here, we have 1, we have 2, we have 3 images. And once we have these 3 images, I mean, for now it's enough. But typically, the rule of thumb is that you should have maybe at least like 50 labeled images with a decent number of annotations per image to actually train a good model. But for now, this will be enough because I'll be providing a fully annotated data set later on. All right. So let's just close it for now. So if you actually see here, you can see that, wait, why is my screen not sharing? Hold on. Can you guys see my screen in the sense that, let me reshare my screen. I think my Zoom is freezing. Okay, now it's back to normal. Check screen again. Okay. Okay, now you guys can see it now. Okay, so what we have here is, of course, the image and the annotation. And in this case, this is the VOC format, but we don't want this format because this format, right, it will actually generate annotations for each individual, a file for each individual image. So if your data set has like 1,000 images, you will have 1,000 extra files to deal with, which is really tedious in terms of data portability. But if you were to open this and just look at it, right, what you will see here is that this is their own format. This is the VOC format. So it also has the width and the height, and it also has like the bounding box itself here, and so on. But we do not want this format. We want the Cocoa format. So what we will actually do is to go back to the scripts. In the scripts folder, I actually provided 4 different scripts to convert to different formats altogether. So we'll be using the VOC to Cocoa scripts in this case. So let's just copy over the VOC to Cocoa folder over to the con annotation example and just paste it here. Then we will drag the unlabeled folder into the VOC folder. It's just, I mean, you guys can see it later on, I guess, but for now it's just, I'm just doing it so that it's easier. Yeah, okay. So in this case, we have the unlabeled folder here inside the VOC to Cocoa.
Hi, it's frozen again.
Oh, sorry, hold on. Hold on, guys, my Zoom is a white screen. Hmm. Okay, it's finally back. Okay, I will try to share again. So I hope this doesn't lag this time. Okay, so once we are here, right? So we can just open this folder in terminal. Then, so the instructions are actually given here in the README folder, in the README file. So this is whatever I wrote lah. So the first thing that we need to do in this case is that we need to actually generate the path.txt. So it is this particular, okay, I think it's lagging again, but okay, damn it. I will try to do, can I fix this? Okay, so the objective for this run, right, is that we want to just run the file according to the instructions inside that readme.txt. I don't think I will try to continue for this part because it would be quite impossible with the screen sharing issue. But if you guys were to actually run the VOC to Cocoa file eventually, what you will get is it's a JSON file that actually includes all of the different labels and all of the different annotations in one. Okay. Then let me try sharing. Again, my sharing is also not working. Hold on. Mm, share screen. Okay. Let me try sharing it again. Okay, it's a bit blurry. I think it's blurrier, but hopefully it's better. So eventually what you guys will get is to get I will not run it just in case. So I'll just show you what the end product will be like. So what you guys will get is the output.txt will be here. Okay. So what you guys will see is that there will be output.txt file here. And then after that, for the other annotation example, what you guys will see is something similar to that. But unfortunately, I think the screen sharing is really bad and lagging for some reason. So I will not continue with this part, but I will try to share. Let's move over to the Colab file itself, which should be better. So let me share back the PowerPoint first. So this should be better. All right, so I'll just move over to the Detectron2 part first. So the instructions for the dataset annotations are all inside that particular file that you guys might have downloaded. So you guys can just follow it and just see it that way. Everything is quite intuitive and everything is quite like laid out for you guys, so it should be fine. So moving on, what is Detectron 2? Can I check whether it's still frozen? I am on like what is Detectron 2 slide? No, I can't even see chat. Hold on. Hmm. Let me try using a different account just in case. Then give me a while. Stop sharing. Okay. Hmm. My entire Zoom is a white screen right now, so please bear with me. Thank you for bearing with me. I finally restarted my laptop. Everything seems to be better now. Let me open my slides again. We'll be moving on to the Detectron2 site for now, since that was giving a lot of trouble. Okay, everyone can see it now. So yeah, getting started with Detectron2. So so what is Detectron2, right? So Detectron2 is pretty much a Facebook AI's library, Facebook AI's researchers library that makes everything much simpler, and it's pretty much a high-level wrapper of PyTorch. PyTorch is a library that is like similar to TensorFlow, but it's more on the research on the research side of things compared to deployment. But Detectron2 is like it's a good balance between like being suitable for deployment because it's like abstract enough, and it's also suitable for development because you can go in and change a lot of things, while a lot of things are also abstracted for you. All right. So for this one, just scan the code. This will bring you guys to the actual the Colab notebook to just see the thing itself, and then we can actually do it together. All right. So I will paste it into the chat as well. I'll wait for a while for you guys to go to this link. Let me know if there's any trouble with this. The link is in the chat if you guys missed it. If not, I will also go to my one myself and start sharing the screen. So you guys should be able to see this. Okay. So for this case, this is my own notebook, so I can make edits, but for you guys probably cannot make an edit. So if you guys want to save this old notebook for yourself, then what you guys need to do is to go to File, then save a copy and drive. Okay, so I'll just do it as well, just to go along with it. So this will actually save it into your own drive itself. Right. Then after that, the next thing that you guys need to ensure is to check your runtime here. Okay, then go to change runtime type and make sure it is set to GPU here instead of CPU, instead of none or TPU, set to GPU. Then just save it. Once you guys have done that, we can continue and just press on connect. So it's connecting to a cloud instance of a GPU and a CPU right now. And what if in case you guys don't know what Colab is, what Google Colab is that it is a cloud instance of a Jupyter notebook that gives you access to temporary storage. It gives you access to a CPU and a GPU as well. And sometimes the GPU can be much better than what you can get on your own computer, or sometimes even better than a gaming GPU on your own computer. So just a fun bit here. If you guys want to see what GPU you guys got from Colab for free, you guys can run this command, NVIDIA SMI. This will actually tell you that in my case, I got a Tesla P100 GPU. But for you guys, if you guys are not a Colab Pro subscriber like me, then you guys will probably get a Tesla or NVIDIA P4 or T4 GPU instead, which is somewhat slower, but still very much better than having to spend your own GPU and run it on your own computer. So after that, we will actually start to install Detectron2. So the good thing about this Colab environment, right, is that it will actually pretty much just have a lot of the libraries already pre-installed, like PyTorch or TensorFlow or other machine learning libraries. So you don't have to actually like set them up and like worry about compatibility issues. So the only thing that is unfortunately not installed is Detectron2. So let's go ahead and just run this cell. So it will actually install the Detectron2 library for this particular instance of PyTorch, which is PyTorch 1.9, which is also the latest one, I think. So it's typically quite fast to install everything. If you guys are getting any errors here, it's probably because you guys forgot to set the runtime to GPU earlier on. So after we have installed the library here, we have to actually restart the runtime. It's just so that everything is properly loaded later on. So after this, we will be importing PyTorch, PyTorch which is Torch and Torch Vision. And then we also will be importing all the Detectron2 stuff from here. So usually these are like, you can read more about them later on your own time, but these are pretty much the ones that we will actually need to import to make the basic use of Detectron2. Okay. Then now we'll be downloading 2 datasets from Google Drive. So this is from my own personal drive. I hope the download limit doesn't exceed, but it should be fine. So let's install gdown first. Gdown is a library, it's a Python library to actually download from Google Drive very easily. And then just run this cell. This should allow you to download all the folders, all the data sets that we need. So it actually downloads rather fast because it's like Google Drive downloading to the Google Colab instance itself. Wait, your screen is frozen from our side or point of view. No, are you guys seeing the downloading one right now? Okay, never mind. Sorry for that. So now we go to prepare the data sets. Okay. So we go to prepare the data set. So what we will see actually here, right, is that we actually unzipped the 2 data sets that we actually have. So we can actually have it here in corn and tomatoes. All right. So for corn, the data folder contains the images of the corn. So let's open a random one here. This will actually open here. So the objective is to identify these little flowers that you see here. This is basically the flower of the corn itself. And as for tomatoes, we actually have the tomatoes in a greenhouse. So this is it's like a greenhouse vertical farm. So there's like tomatoes all over, and the objective is to segment out these tomatoes themselves. And if you were to look into the annotations.json file itself, annotations.json, let's say for this one, right? This is actually the Cocoa format that I went through earlier on in the slides. So just give it a while to load. So you can see like, this is like the full data set, right? So there's a lot of different numbers and like a lot of scary looking things like, so but actually what it is that these are just the things that I mentioned earlier on. Like you see here, we have the images that we also have like the file name, the height, the width, and so on. And then for the annotations themselves, right? We have like bounding box, which is the four numbers that I mentioned earlier on, the area, the category ID, and the image ID. So it's all just the exact same concept, except that it's for a much larger scale. Somebody was asking, what's the purpose of gdown? So the purpose of gdown is that it's for us to download files from Google Drive very easily. So you just have to provide the Google Drive link, and then you just call this gdown command. It will download it into this current instance. So it's actually not required for Detectron2. It's just for ease of use in this case, right? So after we have the data sets, right, the good thing about Detectron2 is that you don't have to write a lot of code. You just write like this particular line, that's it, which is to register Cocoa instances, because our data set is in Cocoa format. So we just call this register Cocoa instances, and then so tomatoes refer to the actual data set name. So the data set will be called tomato in memory. And then this one you can ignore. Then here, tomatoes.annotations.json is basically the annotations file that we have here. We have here right now. Then after that, we have the JPEG images, which is the path to the images themselves. All right. Then after that, we will just call this for both the data sets we have here. So if you guys want more data sets, right, you guys can just go online onto places like Kaggle, or just Google for like whatever object you want, then object detection or instance segmentation data sets. Typically, there will be like data sets that are quite plentiful for most objects like humans or cars. There's like plenty online. And then you just search, if you want a Cocoa format, you just search for like human Cocoa dataset or cars Cocoa datasets, and they will give you a lot of stuff. And if you guys don't manage to get a data set in the Cocoa format, you guys can use the scripts that I showed earlier on that you guys can actually get from the link as well to actually just convert between the different formats. typically the formats that are available online will be one of those formats in the scripts folder itself. So just follow the instructions and you guys can convert it to COCO format very easily. So now that we register the COCO format, we can actually get a metadata here. So this is just to show you guys what the metadata is. So here it's just telling you that it is a COCO evaluator, and the image root is at this particular file path. The JSON file can be found in this file path, and the name is tomatoes. So from here, right, we will just try to visualize the data sets and the ground truths. So for this one, let's just call a dataset. So it's dataset catalog.get tomatoes. So this will actually create a dataset catalog object. So a catalog is like a list of items in a particular set, right? So it's like dataset catalog will basically give you like a long list of like annotations inside this particular dataset. So it's kind of like a dictionary object. So I call it tomato dataset dicts. Then in total, there's like 119 images. So there's like 119 dictionaries inside this particular list. And if you were to look at each individual one, there are keys. That's like your dictionary keys. There's like file name, height, width, and so on. And if you want to look at the annotations themselves, you can just run this, and you will see that this is pretty much the segmentation one, right? So you can see like it's super high resolution annotations. So we have like a whole lot of segmentations like XY, X1, Y1, X2, Y2, all the way. And it's like never ending. So it just got truncated eventually. So this is basically one annotation. So professionally annotated stuff tends to be like this way. But if you were to annotate yourself, it will be somewhat less resolution, somewhat less numbers. But typically you will end up with a somewhat similar performance, only maybe a little worse. So it's okay to annotate by yourself as well. And now let's actually visualize the images and the annotations. So what I'm doing here is to randomly sample 3 particular images from that dictionary and just visualize the images. So this line of code is also provided by Detectron2 themselves, right? So they actually have a visualizer object that will take in the metadata and the image and just return everything that you need to see. So ideally, these are the ground truths, and this is what the model ideally should return after we train it. Okay. And then as for con, we can actually look at this one here. So for con is object detection. So for object detection, what we have to do is to actually just have a bounding box, right? So it will tell you these bounding boxes here. So in this case, it's actually called tassel, because tassel is the more scientific term for these flowers for corn. Then I will skip the object detection model part because it's essentially the same as the instant segmentation model. And I think instant segmentation model will be cooler. But to run this thing, right, you don't have to change anything at all. So I'll actually explain the code in the instant segmentation part. Okay, so for the instant segmentation model, we will actually set up the model here. So the first thing to import is to import a default trainer. So this is like a model trainer with the default settings. And what Detectron2 makes use of is something called a config file. So they have a default configuration, which is just like available just by calling get config. And then the config name, right, is something that you need to provide here. So the config name, in this case, what you will have to do is to look at the model zoo. So let me open a new tab and I will show you guys here. So Detectron2 model zoo. So what a model zoo is, right? It's like a real zoo, whereby if you go to a zoo, you will see different animals, right? So in this case, a model zoo is that you go to this page and you will see the different models that are available for Detectron2. So there's quite a lot of explanations here, but the summary of it is that here you can pretty much see the different models that are available. So for our case, we are doing object detection, right? So this is actually like pre-trained object detection models on a particular dataset called the COCO dataset. Okay, I have a question. Does it mean that we can easily change our models just by using that we use by changing the config? Yes, that's basically the point. So I will show it here, right? So we actually have like different models. Here, R50 stands for ResNet 50. R101 stands for ResNet 101. You guys can read more about it in this particular section. But it's pretty much the same. So basically, these are the metrics. So the higher the AP here that you see, the better the model is. And so like if you want to, let's say we want to use this particular model, the R50 C4 model, right? Or R50 FPM model, we just click on it. Then we will see like the name here, right? So we will see the cocoa detection faster RCNN R50 FPN 1X. So what it corresponds to in this case will be this particular name that we need to have here. So because for instant segmentation, we are not using faster RCNN. We are using this other thing called mass RCNN. So this is cocoa image segmentation with mass RCNN. We'll be using this one, but for object detection itself, you can actually go for this faster RCNN only. Okay. Can anyone link the collab again? Okay. Let me put it in the chat. Hold on. Slash MLDA 2. It's in the chat. Okay. Another question is that can Detectron2 compute performance metric like MA big things? Yes, it can. So I actually have one section later on that I can show you guys where it actually calculates the MAP everything there as well. Right. So just to go back to this instant segmentation one. So if you would see here, so it actually has the YAML file, right? So we can just copy this, right? Then we can just paste it in this case. So if we were to paste it here, it will just change the name. But for our case, we'll be using this particular thing, which is the same as whatever we use here lah. So it's the same thing again. Okay, another question that we have is, can we segment different types of objects in a single image instead of all tomatoes? Yes, we can. So if we want to segment different types of images and different types of objects in a single image, right, we will have to have a data set that, of course, have different categories and different images, different objects that are segmented. And so in this configuration itself, what you will see here is a number of classes, right? So for our case, it's 1 because there's only tomatoes. But let's say we have a data set with tomatoes and maybe apples, then we can change it to 2 if you want to. So just change the number of classes here. So this is the one of the more crucial things that you need to change. But besides that, the other ones that you have to change here are not that much. These are like the default values that it will work decently well. Okay. So max iteration here refers to the number of epochs that we have. So for this particular use case, 500 epochs is more than enough. But for more tough data sets, you can go, I've gone up to like maybe like 5,000 or like even 10,000 epochs, which for me takes around maybe 2 hours for around 1,000 images. So for this one, let's just run it. So this will actually create a trainer object. And this trainer object, right, is actually right now downloading the pre-trained image, pre-trained model file from a library from the cloud, from Detectron2's own servers. Okay. Then after that, it will actually, so you can see here it's actually downloading it like percentage-wise or whatever. So you don't have to worry about the size lah. The size is actually used in this particular instance only. So you can see here that we have like 112 GB available. This number will vary according to your own individual instances. Okay, another question is that for the data set, can also annotate more than one object in the image, right? Yes, definitely. You just have to change the name of the label that you can just annotate it as much as you want. Like there's the unlimited number of categories that you can annotate lah, or like unlimited number of objects lah. Just that your image eventually will get very crowded. Okay. So now that we actually have the trainer file, I actually downloaded the thing as well also. So we can just train it here. So this is just like, so for typical like PyTorch or TensorFlow stuff, right? You guys have to write a lot of code, like what number of epochs, define the optimization, optimizer, define the loss and whatever. But here you just call trainer.train. But of course, if you want to actually change the inner workings and change the optimizer, change the learning rate, etc., you guys can go into the documentation and check how to train it, how to change it. It's quite straightforward as well. So another question is this the state of the art tool used in industry now? So from what I know, at least for my company, yes, we are still using it. But for other companies, some of them, they prefer to use like TensorFlow or PyTorch by itself because it's actually like more customizable. But for those people who just want a proof of concept model, before you actually deploy it into like actual services, you will actually use Detectron2 or like something that's more higher level to actually see whether this idea works or not. If it works, then you will actually like fine tune it later on. Okay, another question is usually how many data sets do we need to train a model well? So I think there's only one data set, but I think you're meaning how much data we need to train a model well. So this actually depends on the task itself. So in my case, right, in this case, we have like we're only training for like one particular instance of tomatoes or corn. So we will need maybe like 50 images and like maybe like 2 or 3 tomatoes in each image to work well. Actually, it depends on your own task. So you have to experiment with that. Another question is that does detection have an API for image augmentation for situations where we don't have enough images? Okay, so for this part, right, there are actually augmentation stuff to actually, there's actually augmentation in the thing. Let me show you guys the documentation. This is like Detectron2's documentation itself. So API documentation. So you can see here like there's like data here, and then there's also data transforms. For data transforms, we have like the different things like to apply it to the different parts. We have like different things like padding, you know. So we have padding, we have cropping, we have transforms, we probably have brightness too. Yeah, we have brightness and stuff. So there is very basic image augmentation that you can apply, which will also apply not only to the image itself, but also to the boxes. Let's say you resize the image, right? It will also help you to resize the boxes. It will also help you to resize the instance, the segments itself as well. So Detectron2 is quite good in that aspect. But for certain more nuanced augmentations, like let's say like cut mix or things that you might be familiar with, like cut mix or like mix up or something like that, it's not supported here, so you have to implement it yourself for that case. But typically the very basic ones are all supported in this case. Okay. So now we'll be moving on. Okay, I think it's frozen again. My screen is frozen and my Zoom is not working. Just let me stop sharing for a while. I'll see if it works again. Another question is, do you recommend using GAN to generate more image to label, or is it better to just find more data? So this is actually, I think, a rather interesting research question by itself. And I think people are actually exploring it. But from my own experience, I feel that using GANs to generate more data, right, it will eventually generate data of the same distribution, the same feature distribution. So I think that it's not as useful, but it can make some impact if you don't have enough, if you have very little data. But if you have a lot of data already, then it doesn't really make sense to use GAN to generate the same kind of data lah. But generally, I mean, if it's very little data, then sure, you can go ahead and use scans. But another easy way that I did was to actually just like copy paste the segmentation, the segments over different images and just generate more data that way. Okay. Here you can see that we're actually training the model right now. So so for me, it takes around 7 minutes to train the model. But for you guys, it might take maybe a little more than that because you guys probably have a little worse off GPU. So that's the main thing about collab, which is that sometimes it's a lottery in terms of the things that we can actually get. Okay, so while the model is training, I'll actually go back to the slides itself. All right, so let me try sharing my slides. This is to explain about the different parts of possible deployment options. So, my Zoom is freaking out again. Sharing. Hope you guys can see this. Okay, you guys should be able to see this. Okay, so for deployment options, right? Let's say once we get the model itself, right? So how can we actually deploy it? Deployment means that we want to make it available to other users to actually use the model. So how can we do this, right? So we can do this by actually using different APIs. Like I'm pretty sure most of you guys are familiar with Flask or Fast API, which is a simple REST API that you can call, and then you can actually just load Detectron2 there, and then you can actually use some of the parts of the code that are inside the notebook to actually just put it into your Flask script, and then you can just run it that way. Another one that I would actually recommend is using TorchServe. So TorchServe is a special library that's developed by PyTorch. And since the Detectron2, right, it is built on top of PyTorch. So Detectron2 models can be deployed using TorchServe as well. So what TorchServe will do is to actually provide a web server, just like Flask, but it's like exclusively to deploy PyTorch models. And it will actually provide you with like a rather straightforward way of actually deploying the models, and it's actually quite robust. And they actually optimize it to handle like batch inferences and stuff. So you don't have to care about a lot of the nitty-gritty details, like how do you handle multiple requests coming in at once or other stuff. But of course, if you want a more customizable approach, you guys can just use Flask or Fast API in that case. And as for the next option, which is for data dashboarding. So some of you guys might not want to actually just have a REST API, but rather to deploy the model using, let's say, like a Python-based web application. Okay, I think it's freezing again. Hold on. I got a feeling this is something to do with the number of participants or either my transcripts. Maybe let me restart my com. It takes like 1 minute. So I'll be back very soon. Just give me a while. Okay, I am back. Thank you for bearing with me once again. I think I've never tried to use a 200 people, like 100 people Zoom meeting, so somehow things are strange. But just let me open the sample thing once again. Okay. Okay, I am now sharing my screen. This should be okay. Okay. So yeah, so now for data dashboarding, right? So just like I was mentioning just now, data dashboarding is something where we can actually just straight away have a data dashboard from Python itself. So there are several libraries for that, such as Streamlit and Dash. So these two are very popular libraries right now, whereby you can just pretty much just use Python to make a web application and just run it on your laptop straight away. So for this one, you can actually incorporate Detectron2 into this. But of course, your Detectron2 must be running on your own laptop lah. But generally, it's quite a nice feature for like rapid prototyping and just to like make a really impressive web application to show for your projects or whatever or your presentation. All right. So now I will go back to my Colab notebook, which has already finished training. So let me share my Colab. Okay, you guys can probably see it now. All right. So yeah. So we have finished training for my case, but I think for you guys, from what I tried yesterday, it might take around 30 minutes. So after we finish training, the next step we can do is to create a predictor. So this predictor, right, it will actually take the model file from this training and actually make a predictor out of it. So the thing about Detectron2 is that it will automatically save the best weights of the model, which is basically the best performing model, into this output folder. So output folder will have this model final.pth, which will pretty much just have all the things that you need to load for Detectron2. If you just run this, it will create a predictor object. So once again, it's a default predictor, but if you want to have a custom predictor, you can just do it that way as well. So from that one, right, let's just visualize some random inferences. So this is using the training set. So I mean, if you guys know about training and testing sets, this is like cheating. But I will show you guys a example from outside the data set itself. So for the data set, after training for 5 minutes on this GPU, we actually get a really good performance that you can see that it managed to identify like a lot of the tomatoes in the image itself. So you can see that it's like really fast and really easy to train. And also it gives a rather decent performance in this case. So if we want to have something that's from outside of this data set, let's just upload an image that I got from earlier. So this is called greenhouse tomatoes that I downloaded from Google. I just Googled for tomatoes in a greenhouse and I got this image. So if you were to run this, right, what you will see here, so this has not been trained on the model at all. So what you will see here is that it actually manages to identify most of the tomatoes in the image, like except for the super far ones, which you can't expect a model to train to see. But as long as you have this, it's like you can see that it performs really, really well already. So a question here is that if I stop the training now, will the whole training data will be lost, or does the trainer.train save the last best weight? I believe that if you were to look at the output, right, if there's a model final.pth or like a last checkpoint, I mean, a model final.pth here, it will probably have the file already. But if you stop the training without a model final.pth, then I think the training progress will be lost in that case. Okay. So here you can see that we pretty much have the entire thing running and like running quite well. Like if you were to train it for even longer using even more data, it will probably be able to detect the segments even better. Like even with this small amount of data, you can see that it manages to detect like the very small little like tomato that you see in this very small little corner that's occluded by the leaves themselves. So you can see that Detectron2 is quite a efficient way of training object detection models and segmentation models in a very fast-paced manner. Another question is that where can we add the code to count the number of tomatoes in the image? Okay, so you can see here, right? Like here I'm printing the outputs from the predictor itself. So in the predictor, what the outputs is actually this entire dictionary. So what we have here is that we actually have the number of instances that you detected. So what you can do if you want to count the number of tomatoes is to just to like go into this dictionary, get the instances and get the length of instances here. So in this case, it will be 22 tomatoes, but for your image, you can just like find the length of the list or like just get this particular variable from there. It's all a dictionary object, so you can extract the information out quite easily and do it for your own use case. Okay. So this output, right, is actually, this is your bounding box, which is your X, Y width height of each tomato. And these are the predictions. And then these scores are pretty much the confidence level of the tomatoes that the model thinks that is present in the image itself. Okay. And then after that, the prediction classes here, in this case, it is all 0 because we only have one class, which is the index 0 of tomatoes. But if you have more than one class, let's say tomato and apples, it will be the 0, 1 or whatever in that case. Okay, another question is that in the config.settings, config.dataset.train is the same. Okay, yeah, so for this case, I'm just using it to be the same, but for your actual case, if you want to change it, you can change it in that way. So what the question is referring to is pretty much here, config.dataset.train and test. So for my case, I don't actually have a test set for this twice data set, so I just put it as the same for this case. But for your actual use case, if you want to have a proper metric and everything, you can change the dataset name to let's say like contest and have a separate dataset that's loaded called contest with a different set of images. Okay. So for the object detection part, right, it is pretty much the same as well. Like we will just train a model. Then after that, we will just get the predictions here for each individual images. And then just now somebody was mentioning about calculating MAP, right? So for this one part, right? So I didn't train the model here, but you can just run this cell to get the MAP evaluation. So because we are using the COCO format, we can actually just use the COCO evaluator here as well. So the COCO evaluator will actually help you to calculate in the way that COCO calculates MAP, the performance on a certain data set. So for this particular case, we will actually use con as a data set and we just inference on the data set. And then it will actually print out the MAPs here everywhere, like your different APs that you can find your MAP from this particular set of numbers that you have. So all these things are once again like the default setting for COCO evaluator. But if you want to change your own MAPs, or if you want to change your own particular metric, or like even at like, let's say accuracy for number of number of tomatoes in an image, you can go inside, change the evaluator, and then output different kinds of metrics from there. So it's all really quite flexible, but also quite abstract in the same sense. Okay, so this is what we have. Then, okay, so besides this, I'll also show you different kind of other models that Detectron2 can actually handle, which I did not cover, but it's possible to do lah. So for example, let's download this image. This is actually a demo from Detectron2 themselves. So once we download this image, this is the image of a person on a horse. So one particular model that they support is called a key point detection model. So what a key point detection model does is that it will actually identify key points on the body of a human. So it's like your head or your spine or your shoulders or your hands or your feet, right? Or your knees. That those are particular key points. And then the model will actually help to identify those particular key points on the model, on the human. So the use of this is in like things like pose detection, where you can identify how a human is posing in an image. So here it's actually downloading the model that's already pre-trained and actually just like calling the prediction right now. So you can see here like it's able to like identify the human here. It has like the shoulder outline, the legs, the pelvis, the neck, and everything there. So it's actually quite a robust model. And then, of course, to train such a model, you will have a specialized key point-based detection or segmentation data set. So that's something that I'm not covering in this workshop. But if you want to, you can just find more details about it online. And typically, like it's all quite well documented also lah. So it's quite okay to do that. Another one is called the panoptic model, panoptic segmentation. So this is one of the segmentation types that I covered very early on in the workshop, whereby the panoptic segmentation will actually color every single particular pixel in an image and I assign it to a different label. So in this case, once we download this model, which is quite big, 261 megabytes, it will actually help to pretty much do a panoptic segmentation of everything there is. Okay, so what you will see eventually in the output is that here you can see that it actually like pretty much assigns this entire area as trees, and then you have a horse, you have a person, etc. So for all of these things, it's dependent on your own data set. If you want to have a data set that identify cars, you can do that. Identify roads, the sky, the background, buildings, or anything. It depends on the data set. Just feed it the proper format, and then it will train it for you, and then you will get all of these very easily. It can also do panoptic segmentation on a video. So for this one, I'm not sure whether it will download quite well. It should be okay. So for this particular video, it's actually downloading rather fast. So Detectron2 also supports video segmentation, video instant segmentation and stuff. So this is a demo that they actually have from the official Detectron2 instance library. So it will actually run Detectron2 on each individual frame of the model, of the video. So it actually takes quite a bit of time in that sense. Like you can see here, I think it's like around like 3 minutes or so. But once you actually finish running this, you can see the output like it's actually a very cool like thing like it's able to actually segment out the video, just that it's not in real time. It's not a real-time segmentation of the video, so it's not as good as other models that are out there lah. But then after that, if you want to download this eventually, you can just download it using the videos, using the files to download in this case. Okay, another question is, what is the FPS performance of the model used in the video segmentation? Okay, so for this one, because for this particular case, right, we're not doing it in real time. So Detectron2 is running on individual frames. So the FPS performance is pretty much based on the video itself. But here is so for each frame it takes around, I'm not sure, it's definitely less than 1 second, but it's around between the millisecond to second range for each frame. So it's not as fast as other things like YOLO or some other stuff that can do in real time. But in terms of if you have time to waste, then you can just run it. But it's not as good for real-time performance from like cameras or like camera feed for that matter. Okay, so that's pretty much the end of this particular notebook. So I will stop sharing the screen, and this is also kind of pretty much everything that I have to Let me share my thing here again. So it's pretty much the end of, okay, before that, I'll cover the Android one, the Android version. So some of you guys might actually be interested in actually deploying a machine learning, deep, instant segmentation model or detection model on Android. And Detectron2 actually supports that, surprisingly, but actually has a special library called D2Go. So D2Go is pretty much the same as Detectron2, but it's optimized for Android. And so they actually provide boilerplate code for a very basic Android app, which is able to like once you provide the model, it can detect, it can like even do live, but I think the live version is around like 1 FPS or something, so it's quite bad. But for a static image, it's able to do that very well. So you can use this in your projects or like your school course or something like that if you want to have a nice demo to show for your projects lah. Yeah. So this is everything that I have to cover. So if anyone has any final questions, please feel free to ask. Okay, so one question is, so in this tutorial, Detectron2 is used as a well-packaged library. What if I want to add some customization, like adding an additional conf layer for RPN head? So if you want to add an additional layer for your RPN head, then Detectron2, I believe they actually support that. But the case with this is that you won't be able to, of course, use a pre-trained model anymore, except for maybe like the backbone itself. But Detectron2 can actually help you to add the models, but you have to go into the documentation to see how it actually does it. And for that, it will probably not be like preloading a custom a pre-made config. So you have to change your configuration as well. But they do support modification of models and using custom models as well. Yeah. But anyone has any other questions? Any notable advantage of Detectron over YOLO? I would say the advantage of Detectron over YOLO is that uh, Detectron2 with like faster RCNN or mass RCNN can do both segmentation and detection, and also that it's in some instances it will give you a higher performance than YOLO. But if you're not caring about absolute performance, then I believe YOLO will actually be better in that case. But YOLO tends to be a little more verbose in terms of the code to write lah. So Detectron2 is more abstracted. So it's easier for beginners and like people who just want a proof of concept model to pick up and just use straight away. Yep. So that's the main advantage of Detectron over YOLO. So besides that, so that's pretty much the end of this particular workshop. So if anyone has any questions, just ask. If not, the links to the slides and files and notebooks are found at the end of the form, which is this feedback form. So it's just a feedback of this particular workshop. So I do apologize that my Zoom kept on freaking out, but I'm not sure what actually happens because I have never experienced that before. But yeah, besides that, I hope everyone had a good time just looking at the different possible implementations and stuff. Okay, another question is that can we implement this segmentation on Python notebook or shell? So yes, you can, just that you will have to install Detectron2 on your own computer or something, which works for, I believe, for Linux and for Mac. Detectron2 is installable, but for Windows, you might have to go through a few extra steps. For a typical, I mean, Python notebook or shell, as long as you have Detectron2 installed, it's fine. Yeah. Of course, if you want to train properly, then you will probably want a GPU as well. So usually for Colab, right, Colab provides a free GPU. So usually the recommendation is that you will use Colab to train your models, to actually put it into your computer after you train it for like inference. Okay, other frameworks better than YOLO for real-time detection. For that part, I think I'm not really familiar with other frameworks besides YOLO for that. But usually there's like quite a few different frameworks out there that you can explore. One way to actually optimize for real-time detection that I'm aware of is to use things like TensorRT. So TensorRT is a special library that's actually used to actually like optimize the models and like the different layers. But TensorRT itself, you need an NVIDIA GPU if I'm not wrong. And also it only works for certain kinds of layers. So not all kinds of layers that might be present in special models might be available for TensorRT to optimize. But from what I did for my previous projects, I actually did a detection model on a Jetson Nano, and I actually used TensorRT to deploy it, so it was able to do real-time detection very well. Yeah. So yeah, thank you for attending this workshop. Yeah. So and then MLDA feedback form is there. If you want the slides and the links and stuff, it can be found at the end of the form. Or if you guys want to actually go on to the MLDA GitHub, you guys can find it there as well. Do you have any recommendations for customizable, faster or mass RCN implementation, PyTorch or GitHub? Actually, I think I do. Hold on, let me share my Chrome then. Well, you guys can see. Yep, you guys can see. Yes. I think. Right. And so this is one thing that I'm rather familiar with. So this guy is basically like he has a lot of pre-trained models and stuff. So he has a lot of different models that are already available and like trained on different data sets. So and then he actually provides quite a few like training and other training and inference API for his models also using PyTorch. So it's quite a good thing, but it can be quite complicated at times. But if you want a custom or like if you want a custom implementation of something, then this is the place to go for PyTorch, I feel. Yeah. Anyone does have any other questions, then that's all for today. I will be staying just in case anyone has any other questions. Yeah. Otherwise, you guys can leave. Thank you for attending. Another question is that if I want to do real-time object detection for a device like a drone, this will not be recommended, right? Yes, it will not be recommended if you want to do real-time detection. For things like a drone, okay, the thing about drones is that you would probably be using either a Raspberry Pi or a Jetson Nano. And if you want to do real time on a Raspberry Pi, it's really, really hard to do so unless you want to do like 1 FPS. So I would recommend using at least a Jetson Nano or some kind of GPU enabled microprocessor to actually run some kind of NVIDIA library there. And then in that case, you will probably want to use YOLO or some other real-time detection library. Yeah. What do you recommend to learn to the person who just started learning AI? Okay, what I would recommend to someone who just started learning AI is this thing called Fast AI. So Fast AI is this what I feel is actually how I got started on learning AI as well. So for Fast AI, it is like a course and also it provides you with all of the notebooks that you can run in Colab themselves. So you can learn about detection, segmentation, classification, not only for the different not only for computer vision, but also for like natural language processing and stuff. So they will show you everything that you need to learn, all the basics of it. So it's really quite cool about that. Let's see other questions. Okay, my Zoom is freaking out again. So I will just look at my chat from my other computer. Uh, YOLO will be the least computationally expensive, right? Yes, YOLO will probably be the least computationally expensive right now. But I think there might be more things coming out soon. Who knows? And probably maybe YOLO V3 or V4 might be better. Yeah. There's a lot of YOLO versions right now, but it's arguable that whether it's a new version or just optimized or not. And thank you for attending, guys. That's all, I think. If anyone has any other questions, please feel free to ask. If I were to simplify, detect contours instead of heavy classification, would a pi be sufficient? If you want to detect the contours, I believe I think this it's quite hard to answer straight away. It depends on the kind of contours that you want to detect and the kind of object and the environment that you will be operating in. But if you want to just detect contours, then I think that perhaps OpenCV might be the first way that you might consider first, because there are contour detectors on OpenCV, which does not require much computation. And they can probably run in real time quite well. So you can try that first. And if that doesn't work, then you can probably try other libraries. But for that, a Raspberry Pi, I think should be sufficient. Yeah. Oh, okay, sure. Hold on. Let me paste it in the chat. Another question is TensorFlow or Detectron better for segmentation? I believe if you are someone new to this, then Detectron is probably easier to learn and create a model straight away. But TensorFlow would be better if you want to customize the different aspects of segmentation itself. If you're just looking for like just a typical segmentation thing, that Detectron is probably easier for that case. But for both of them, there's a lot of tutorials online that you can just look up and just do it quite fast lah. Just that the TensorFlow will probably require more code in the aspect. I think another question that I saw is that can I use segmentation on the Raspberry Pi? Uh, I think that segmentation, if for this segmentation on a Raspberry Pi, probably not. So for my own internship, what I did was to actually get the data from a Raspberry Pi first, but then I actually ran the segmentation in the cloud itself. So I use AWS for a compute instance, that's a CPU instance. Then I took the images that I get from a Raspberry Pi and uploaded to AWS that way. Yeah. Typically, Raspberry Pi cannot really run any kind of segmentation or like detection model in a real-time manner. It will probably take like quite a long time to just get on one image itself.